Hello again. We are now going to proceed on to the final unit in Math 2345. Although before we do so, after taking the Unit 3 test, you might find this to be a little bit appropriate. Hey, math can be pretty boring at times. We should try to make it a little bit more entertaining along the way if we can, while still learning a good few things. Now for this final unit, we're going to go slightly out of order with regards to the textbook. We're taking chapter 13 and we're moving it ahead of chapters 9 and 10. You don't have to do it this way if you don't want to. You can choose to cover 13 after 9 and 10. The reason why in the lecture video playlist on Blackboard and other locations, we have chapter 13 placed as being ahead of the other two chapters is because chapters 9 and 10 focus on hypothesis tests, and hypothesis tests essentially take everything that we've gone over and put all of it together. And so it stands to reason, let's take the thing that puts and brings everything all together as the final two chapters for the course. The other thing I'm going to note, and if you are a student in my course beginning with the spring of 2025, which is when this is recorded, technically January is the winter, but you get the idea. Starting with this year, you will no longer have to compute many of the things in chapter 13 by hand. It is very important that in this course, given that, as is stated in the title, applications to business, we should focus not only on the applicability as much as we can, but how we would perform it in the real world. And so in this case, you will very usually use a program like Microsoft Excel or Google Sheets to compute what this chapter goes over, linear regressions, and correlation coefficients, instead of doing all of the arduous work by hand. Prior to 2025, students had to compute it by hand, but starting with this year, and as I will show you in this lecture, you will be able to use Excel or Google Sheets. Most of you should be able to access Excel without paying for it. However, you'll be able to use Google Sheets as well so that you don't have to pay for it. And something extremely important to keep in mind is that on the Unit 4 test itself, instead of you having to pull up an Excel workbook or a Google Sheet to compute a correlation coefficient or a regression label, you will instead be given the outputs from an Excel workbook and then go from there. So if you're worried about whether or not you'd be able to access Microsoft Excel or Google Sheets for the Unit 4 test, or if you're concerned whether or not a proctoring service might flag you for that, you will not have to worry about that at all, for the simple reason that you will be given the outputs. The reason why I'll be going over how to program them into Excel and Sheets in this lecture is so that you're going to be able to apply that to the real world and know the common interpretation mistakes that are made when working through those. So with that, let's go ahead and get started with the material. When we are doing linear regressions, you can do what's called multilinear regressions, which will involve giving multiple input factors for any given output. So for example, suppose that we are trying to predict a home price based on a series of inputs, and we decide to use what's called a generalized linear model. Now that would take in the big assumption that everything's linear, which is not necessarily going to be the case, but think of some factors that might impact a home price, such as number of bedrooms, number of bathrooms, the total area of the house, what school district it belongs to, and many other different factors. We might in the real world want to take these factors and see how they relate to our output, or our dependent variable, what we're trying to predict, in this case the home value. So we can perform a series of linear regressions for all of our factors and then combine them together. But in order to do that, you have to start with a simple linear regression. For this course, you're not going to have to do a linear regression for multiple inputs. We'll start with one input. And the other reason is if you know how to do it with one input, it'll be very easy to quickly learn with Excel in a different course or Google Sheets or any other program how to do it with multiple inputs. Now, suppose that we're trying to predict a home value based only on the number of bedrooms it has. It's not going to be a great model, but let's use it for the sake of argument. Suppose that a house has 2 bedrooms, and then we predict it based off that value to be worth $275,000. Now, it's entirely possible if you listen to this video 3 years from now, that might be $4 million, because who knows where that housing market is going, wink wink. But for the sake of argument, let's take the $275,000 figure. In that case, suppose the actual home value was $280,000. We'd then have a $5,000 difference between the value that we predicted, $275,000, and the actual value, $280,000. This $5,000 difference is what we call our residual. Now, when we do a simple linear regression, we're going to have our y-intercept. In this case, we call that b naught. A b just represents one of our 2 values. Now, if we have multiple input factors, then we might have a b1 for the first factor and a b2 for the second factor, and so on and so forth. But for this course, because we have just one input, the b1 corresponds to how much that input affects our value. So for example, our model might predict that a home should have a base value of $200,000 regardless of the number of bedrooms it has. So in that case, the b naught, or b0 technically, if you wanted to refer to it as that, would be $200,000. And let's suppose for every bedroom we added to the house, it added $37,500 of value to the home. Well then, that's how we get the input of 2. 2 times 37,500 gives us $75,000. Added to the base $200,000 gave that $275,000 figure. So when we do our regression, the question is, where did those values I just made up come from besides my bunghole? In the real world, we want to get the best fit that we can get. The more accurate that our line is in predicting these 2 values, the better. But the question becomes, how do we do that? What criterion or set of criteria do we set in order to get those values to be what we might call best fit? Because the other problem we might have is if we go to look at our line, we might be able to tell a very, very bad line from a very good one, but it can be much more difficult to do that when we have 2 lines that are very good. And so to explain this, it's best to work with a visual. So, I'll go and zoom in first on our visual here on the left. So, we first must define what it means for a line to be a best fitting line. We cannot use a subjective measure here, because if you try doing that, suppose you go onto Wall Street and you do that, you're going to get your clock cleaned into next week, frankly next year at that rate. So let's suppose here we are trying to plot the relationship between the student population in thousands and the quarterly sales in thousands of dollars, say of textbooks. So let's suppose I asked you to eyeball a pretty good regression line, and you decided to give me a line like this. Most of us would look at that line and think it's a pretty good fit, but now suppose I gave you another line, let's suppose this red line, and it looked like this. Which one's better? Well, to the naked eye, it might not be immediately clear which one is better, and if we were all in a classroom, which isn't the case for an in-person class, we could do a show of hands to see who thinks which line is better, and it's pretty unlikely that you're going to get the whole class to agree on which line is better. And it's not because some people are necessarily right or wrong because of better or worse vision, but because to the human eye, these lines are very similar. As you can see near the center of these 2 lines, right about here, there's not really a meaningful difference between the two. On the other hand, on our lower end, it is our red line that gives the higher prediction of quarterly sales, whereas over here, it is the black line that gives the higher prediction of quarterly sales. So let's suppose you look at these two extremes and you say, well, on both of our extremes, the black line does a better job of predicting the actual value. So clearly, the black line is the one that's better. But there would also, by another token, be a relatively straightforward argument one could make for the other direction. Let's instead look at ones that aren't quite near the center, but not near the extremes either. What about these dots and these ones? Well, to use a different color here, if we look at our ones a little bit to the left of the center, so the lower values, but not the low outlying value, notice how for our red line, the red line does a better job of predicting two of these three values than the black line does. Whereas, for the upper values, when these two are lower, as you can see, the red line does a better job of predicting them than the black line. So although the black line did a better job for the outliers, while both of them were about the same for the two in the middle, the red line did a bit better for ones that were a little bit away from the middle, but not too far away. So how do we weigh these dots? What if we heavily value the outliers? Or what if we want our line overall to do a pretty good job of predicting everything? What criterion do we use to evaluate which of these two lines is better? And before, one might look at this and say, oh, well, who cares? They both look pretty similar. We can go with both and have no problems. We'll be good to go. Well, let's look at our extremes to, again, really see where we run into problems. If we use our lower end, this difference might not look like much, but now compare that to our axes. Up here is right around 60,000. I'm sorry, 60 with 1,000. Yes, $60,000. This one looks closer to 50. So that is a difference of $10,000, even though it might not look like all that much on that end. A similar story occurs up here. And so as you can see, the importance of getting a line that is a best fit becomes more and more important the further away we get from the middle. And this is especially true because we often try to use our linear regressions to predict future values. Well, by definition, the future is not going to be the same as the present center. And so we could be more likely to be out on these two ends. Therefore, even small differences can have quite pronounced values over, say, predictions of home values over time. For example, suppose these two lines were instead predicting home values, and we thought, oh, they're about the same, let's go with the red line. But it turns out the black one did the better job up here, year on year. Well, guess what? That $10,000 is going to compound on itself every single year. So once you get out by a decade, it ain't $10,000, it's at least $100,000. So you might say, fine. How do we decide which line is better? Well, here's what we're going to do. Let's specifically focus on this dot right here. What we're going to do is define the residual like above, the distance between the prediction and the actual result. So that's going to be that distance right there. So we have this residual because it's a distance, it'll be positive. Well, what do we do with it once we have this residual? Well, we can do a few things to it. We can multiply it by some number, we could divide it, we could add, we could subtract. Let's start with adding and subtracting. You're adding or subtracting the same fixed amount to everything, so that doesn't matter. You might say, fine, let's take all these residuals at face value. Well, here's the problem with doing that. If we take all of these residuals at face value and do nothing to modify them besides ensuring they're positive, what we're saying is any additional decrease in accuracy should be weighed the same. But as we can see, to use the example all the way at the top up here, that $10,000 difference compounded over a decade becomes very, very large. Whereas on the other hand, near the middle, if you're off by only just $10, not even $10,000, just $10, well, $10 over a decade becomes $100. So based on this example we have here, we should be much more cognizant of differing residuals the further and further away we get from the middle. Especially so, the further and further away we get from the actual result. Because again, one of the main reasons of these linear regressions is to help us to predict what's going to happen in the future. A lot of insurance models are based off of this, or Wall Street hedge funds, companies projecting costs forwards, and many other things of the sort. What good is a model if we can't use it to predict anything? Even if a model does a good job explaining the past, that doesn't mean it will do a good job explaining the future. And so we want to weigh these residuals that are larger by a higher amount. How do we do that? Well, the answer is simple. We're going to take this residual, so the difference between our actual and predicted values, and we're going to raise it to some power. So let's call this residual, we'll call it delta, just for the time being. We take this delta, we're going to raise it to some power n. Well, what should n be? 2? Should we square it? Should we cube it? Should we raise it to the power of 4, 5, 6, 7? Which one do we pick? Well, suppose for the sake of argument we raise it to the power of 4. Well, that's the same thing as squaring it twice. If we raise it to the power of 6, well, that's still going to be a multiple of 2. It's an even number. On the other hand, suppose that we cubed it. Well, that's the same thing as squaring it twice, then multiplying it by itself one more time. So it's going to simplify down to we either raise this by an even power or an odd power. And from there, we run into one more circumstance. Suppose we raise something by an odd power. If we do that and the number is negative, we return a negative. So therefore, suppose we took this distance up here, and we're doing it with our red line. As you can see, let's call this delta 1, and let's call this delta 2. If we just simply took delta 1 minus delta 2, they're going to cancel out because one's positive and one's negative. So we have to raise it by some kind of power. And if it's an odd power, those two will cancel out because one becomes positive, while one becomes negative. So we have to raise it to an even power. If every single even power is a multiple of 2, that leaves us with one option. And that is what's called, what we have on the right here, the least squares method. The idea behind the least squares method is, at least compared to the very in-depth explanation that I gave, much more straightforward when compared to this definition. We want to penalize a line that does a very bad job of predicting values pretty far away from the mean, or just bad predictions in general. And we also want to ensure that our line overall has a good fit, meaning we want to minimize these squared residuals. So you might look at this and say, well, fine, but how do I implement this? You've given me a criterion. What am I supposed to do with it? It's kind of like if you're in an office and someone gives you a big stack of paper and they say, have fun. You might say, well, what do you want me to do with this? Even if it's something useful, where do you go from there? Well, from there, in order to identify a formula for computing this, you have to use calculus. Calculus is not a prerequisite for this course that all of you had to take. Some students took it to satisfy it. A lot of students didn't. But the good news here is you don't have to know the calculus behind it to get the formula here, because the visual example will suffice. Instead, we can go straight to the formulas themselves. Now, prior to this year, prior to 2025, you needed to write this down, and you would have needed to know how to compute this. Starting with 2025, you no longer have to compute that by hand. Because again, we're trying to ensure that this course has a strong application to the real world and that the skills you're learning can be easily applied to your life. And to that end, it's important that we keep the applications how we might reasonably do it. If you're trying to consider a series of factors impacting home prices, you don't want to sit here and spend 30 minutes every single class lecture or study day or anything you're doing on the job computing a regression for one of your possible combinations by hand. Because then by the time of 8 hours of work have passed, you'll have tested a grand total of maybe a few possibilities for your model. After all, some factors could impact your result, some might not. And so to this end, what's going to happen in this course, as I mentioned at the start of the lecture video, you will be allowed to use Microsoft Excel or Google Sheets to compute these. The way it will work is for web work and the number 4 practice tests, you should use Microsoft Excel or Google Sheets to compute these yourself. If you're unable to access Microsoft Excel or Google Sheets, I suppose it would be okay to use an online calculator for those, but I would really strongly recommend that if you're not able to access Microsoft Excel, use Google Sheets. They're completely free. So that way, when you're on the job or in a class beyond this, that you will be able to perform those computations and not have to go through all of the very tedious busy work, whilst also having a very clear paper trail so that if something goes wrong, you can easily check your work. Now, for an in-person lecture, I would simply pull up the Excel document, show it on the screen, technically with multiple screens, and be good to go. Because in the lecture hall, you'll have the multiple screens. However, for the YouTube video, it'll want one screen. So what's going to happen is when we go over the problems, I will bring the work over and paste it onto the whiteboard so you don't only have it for reference with the filled out whiteboards, but will also be able to easily check your work against it. What I will do is if any point a formula is entered, I will put below the outputs exactly what was input into it, so that way you can easily reproduce the work to double check things as well. Because when doing these linear regressions, it is very easy to make a mistake when entering an input or interpreting your results. And so to that end, being familiar with the processes to create them will help a lot. So these two formulas come from calculus. You don't have to worry about writing them down. It's the next part that you're going to need for the web work and the practice test. As I mentioned at the start of the lecture video, on the Unit 4 test, what I will do is give you the outputs as you'll see them here in the lecture video and as you'll see them on the Unit 4 practice test answer key. You'll see a table with the inputs, you'll see the outputs, and then right below them a label of what was input into them. Now, for correlation coefficients, we'll come back to that in a moment, but you should still write it down. When you go to Microsoft Excel or Google Sheets and you type in equals, in this case, LIN for line, EST for estimate, it will then prompt to tell you what parameters to input into it. Something extremely important that you need to have written down. Give it the Y values first. So in this case, you're going to have a table. So for example, let's suppose you had one like this. So you had 1, 2, 3, 4, and 5. If only the course was that easy, then we'd all have hundreds. Well, I wouldn't because I'm teaching it, but presumably everyone else. So let's suppose this was your table, and you had the easiest linear regression the world has ever seen. Well, aside from doing 1, 2, and 3. So in this case, you have what we call arrays. So this is going to be one array, and this is going to be another array. So for example, let's suppose the first column is the B column, and your second column is the C column. Something you can do is on Microsoft Excel or Google Sheets, you can directly input these into columns X and Y to make them very easy on yourself. If you'd like to do that, go right ahead, because on Microsoft Excel, you'll be able to use columns X and Y, whichever you prefer. But to use the ones that you're going to see in this lecture, suppose that we label them as columns B and C. And then let's suppose these correspond to cells 3, 4, 5, so let me try that again. Yeah, that's right. I'll move them down by 1 though, because that's technically your header. So you call them cells 3, 4, 5, 6, and 7. Then in this case, what we would say is that your X value of 1 is in cell B3. Now, for any of you who have used Excel or Google Sheets before, you're probably looking at this and thinking, Professor, can we just have this be the test? You tell me what's in cell B3. If only life was that easy. No, the reason why I'm bringing this up, again, there are some people who may not have used Excel or Sheets before. If you want to reference all of the X values, you're going to go, so to scroll down, this is going to be from B3 all the way to B7, and you do not have to include the header row. And so, in a similar vein, the second column here, so our second array, goes from C3 to C7. If you have never ever used any kind of a spreadsheet before, then I strongly recommend brushing up on just the very simple basics of that. For this course, all you need to be familiar with is how to reference a row and use linear estimate and correlation, but particularly linear estimate. So why do I bring this up? Professor, this is too simple and easy. What's the point of this? Well, the reason why is when you're doing the linest, it's going to ask you first for the known Y values. So when you go into Google Sheets or Microsoft Excel, again, you can use either. They'll both be the exact same for this application. What you're going to do here, if you want to do a linear estimate of this, you would put linest, and you're going to do the Y values first. So C3 to C7. And then you're going to pass over your B values, which correspond to your X values. So you're going to go from B3 to B7. When you do this, what Excel is going to do is highlight the columns as you're passing them, so that way you can very easily visually see that you are passing the parameters you're trying to pass. That's all you're going to have to do. Now, once it does this, in the cell where you input that value, it's going to output two values next to each other. So for this one, as you might be able to look at that and clearly see, the Y value is the same as the X value. It is literally Y equals X. Just about the easiest line we could get. Although if you wanted to put it with your slope and your y-intercept, it would be y equals 0 plus 1 times x. Now what happens when you get these outputs? This is the single most common mistake that will be made with regards to reading the outputs from this. It is not going to give you B0 as the first value. It will not do that. Instead, it's going to give you B1 as your first value. So it's going to output B1. There will be a little bit of a space. And then in the next cell, it's going to put B0. The number one mistake that students will make with this is they'll just take that and input that as their answer for B0 and B1. That is, these two values will get flipped, which is the same thing as flipping it as if it was across a mirror. So please, 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 take very well care to ensure that you know which value is which. Once you have those two values, you just simply put it in the form like above. So for this particular line, we would have y is equal to 0 plus 1 times x. Nothing very difficult about that one. Obviously, if x is 1, 1 times 1 is 1, plus 0 is 1. If x is 3, 3 times 1 is 3, plus 0 is still 3. Very simple and very easy. Now you might say, well, okay, Professor, fine. Can you show me what that might look like in Excel itself? And so to directly paste that over, just typing it out here. Sometimes Excel's going to give you a bit of a goofy looking output. So I'll just copy paste this over. If you take that table and you paste it like this is just 0. If you ever see this, that is 0. Here, let me make that a clearer one for you. Again, notice we pass it our second column first. If you instead pass it the x values first, again, it's as if you're flipping it across a mirror. So ensure you pass it your y values first. Also notice how, as I've shown up here, it gives you B1 as your first value and B0 as your second value. So just ensure when you are using Google Sheets or Microsoft Excel that you're careful to first pass it the y values, and then when you're given your two output values, that you know which is which. So with that, what I recommend you do, if you are at any kind of a computer or laptop right now, I'd recommend pausing the video and opening up Microsoft Excel or Google Sheets. Again, you don't have to pay for it. If you do not have access to Microsoft Excel through Texas Tech or some other institution, you are able to pull up Google Sheets. You might not even have to have a Gmail for it. But in any event, anyone would do. And again, as I mentioned, and as I will promise to you, you won't have to do this directly on the test itself. You'll be given those outputs on the test itself and then be asked to interpret them. So with that, assuming that you have an Excel sheet or Google Sheets open, we're going to go up to a couple examples for you to work through both of them. And then we will go through how to get these in the spreadsheet. All right. So for these ones, using the sheet, again, I'm going to copy paste over the work. We're going to start with the first one. Again, you're going to take your x values and your y values and input them into your table as so. If you'd like to take these two and center them so that it's more aesthetically pleasing, go right ahead. On the test itself, it's just going to show as that because it's the default formatting. So notice how we take our x values of -1, 0, etc., and we input those into our first column there. And likewise, we do the same for the y values of 0, 9, 13, 20, and 24. Once you've done that, you can go ahead and do your output. Now, do not necessarily input exactly these letters every single time. If you start from column A, then of course the column reference is going to change. So if it throws an error at you, double check that you're referencing the right columns. Again, when you're typing this out in Google Sheets or Microsoft Excel, it will highlight the column you're referencing as you type it. So that way it should hopefully be very clear that you're referencing what you're trying to reference. Once again, notice that it gives you B1 as your first value, meaning this is not going to be the first input on Blackboard. I'm sorry, for WebWork. It'll be your second input, and the second input will be the first. So if you go into WebWork and for B0, you put in 1.809717, it will mark it as wrong. So when you're doing these WebWork problems, if it is not marked as correct, the first question that you should ask yourself is, did I accidentally flip my B0 and B1? So if it marks them as wrong, flip them around, and see if that gets the answer marked as correct. If you do that on the Unit 4 test, it will not be worth full credit because that would therefore change your whole prediction since they're all being mirrored. And of course, it's not hard to see how these could result in quite significant financial problems, shall we say, if the wrong regression formula was used. You might think, changing up two numbers, how could that possibly cause a problem? I mix up one conversion, what's the issue with that? Well, there was actually an issue between a metric conversion and an imperial conversion with regards to a NASA spacecraft. You can certainly Google it up. And the conversion failure caused, shall we say, a catastrophic problem with the spacecraft. It is not hard for small errors to compound very quickly. So just, again, number one mistake, ensure when doing this that you do not accidentally flip up your B0 and your B1. So again, your B0 is roughly 5.599, and your B1 is about 1.810 when rounded to the third decimal place. For the second example, to paste over its work as well. And again, if it's an in-person lecture, you just see me typing it, and then you would see this. So as you can see right below it, I put what I entered in there to provide those outputs. Just like before, you enter your data values in as a table, and then you do a linear estimate based off of the values in those tables. Again, ensure that you pass the y values as your first array. So notice how these values are the first array, with the x values being the second array. Once again, do not accidentally put in this value as B0. That is wrong. Always ensure you put that in as your B1. And then this as your B0. So if you wanted to take this one and put it in regression equation form, we might say that our y is going to be equal to the predicted y value, that is, so we could call that y hat, is going to be equal to our B0, which we have listed as the 2.6976. So we'll just put 2.698 times, plus the x value we have times its B1 of roughly 230. So if you wanted to put them in regression equation form, that's how you do it. Very simple and very straightforward. And then predicting a value is very easy. So if you want to predict an x value for 15, you plug in x equals 15 and go from there. Again, with these, you can very clearly see having to do this whole thing by hand would have been just not fun. It didn't used to be quite that ugly for prior semesters, but hopefully being able to use Excel here will be much easier. Just again, be very, very mindful of the pitfalls of using Microsoft Excel and Sheets and accidentally getting your answers flipped up. So with that, those are the examples that we have here. You're going to find that going over these is very simple and very straightforward with regards to Excel and Google Sheets. As long as you ensure that you correctly pass your inputs, you shouldn't run into much of an issue with getting your outputs. Now this is, I would say, the first half, but we've already gone through a majority of the lecture, so we'll say the front end of today's lecture. The other part is, well, okay, suppose that we have our regression line, and we want to ask ourselves, how strong is the relationship between our input value, say the number of bedrooms, and our output value, say the price of the home? Well, if we come back over here, we have the correlation coefficient formula. Now, for the correlation coefficient one, it's very simple and straightforward. you pass in your two arrays. And here's the good news. Suppose we want to do the correlation coefficient for this table that we have here. So we pass it B3 to B7 and C3 to C7. I meant to put in 7 there. It's okay if you can't see it. I'm about to copy and paste it over for you right now. Here we go. Let me go ahead and copy paste this right now. So let's suppose we took this one right here and we computed a correlation coefficient of it according to Excel. It says that. Now you might look at that and say, it should come out to be 100. At first glance, yes. Let's suppose you flip these around though. And this is the part that's more important to take away. What happens if instead you gave it the y values first and then the x values? Guess what? They're the exact same. What this means is if you instead do the correlation from the y values to the x values, you're going to get the exact same correlation coefficient. And what I mean by that is this. Suppose we have our relationship like this. I'll use a box to make it better. Suppose we have our display for our x and our y, and to switch the color for the line. Suppose that this is our line. As you can see, very nice and diagonal. What happens if we accidentally flip our x's and our y's? Well, what that means is we're just reflecting it over itself in this case. So it's the same thing. Now you might look at that and say, so what? What if instead the line was this? Now what happens if you flip the x and y? So suppose we did flip the x and y, and you instead got a line that looked like this. Well, guess what? When we're doing the correlation coefficient, we're not trying to predict a value. We are simply trying to evaluate the relationship between the values. What this means is even if we provided the x values before the y values, or I suppose we do the y values before the x values, you're still evaluating the relationship between the values themselves. So when you're doing a correlation coefficient computation with Excel or Google Sheets, you can pass whichever set you want to pass in first. You're going to get the same output either way. That is, you'll be good to go no matter what. So that is, there aren't really any pitfalls to the correlation coefficient besides second guessing yourself or anything of the sort. So at that point, you might say, fine, what exactly is the correlation coefficient though? What is the point of evaluating that thing? Well, let's get to that. So here, we have a correlation coefficient, and then we have what we call r squared. R squared is the amount of variance in our dependent variable y that is explained by changes in our independent variable x. To use the example of the house, we might say that the r squared is the amount of variance in the home prices that's explained by changes in the number of bedrooms of the house. And so anyone could very quickly see the value of that. We could see how much adding more bedrooms to a home changes its value, or how many bathrooms could change its value, or lot size, how thick the walls are, is there an air conditioning unit, a heater, are there solar panels, anything of the sort. We can see how changes in that impact our dependent variable. So then you might say, fine, what's the point of this correlation coefficient? What's this r for? Well, the r squared explains the variance. The r tells us how strong the relationship is. You're going to need to have this written down. If we have a very small r value, somewhere from say 0 to 0.2, then we have a pretty weak relationship between the two of them. There might be a relationship, but it won't be a strong one. So just because one increases, it doesn't mean the other one does. Then from 0.2 to 0.4, it's a weak relationship, so getting better, but still not exactly awe-inspiring. Once our R value gets to about the halfway point between 0 and 1, then we say it's a moderate relationship. And then we get to 0.6, 0.8, it's a strong relationship. 0.8 and above, very strong relationship. In the real world, it's not all that common to see R values from 0.8 to 1.0 because usually there are multiple factors acting on our dependent variable. To use an example that could be very relatable for all of you, you might be trying to see what impacts my exam scores. Some things that might come to mind is how much time did I spend studying, or how good was my professor. But there are going to be some other inputs. How much sleep did you get the past night? Are you hungry? Are you sick? And many other different inputs. Although one input might have far more of an impact than all of the rest, doesn't change the fact that it's going to be difficult to find very strong relationships in the real world. So when you do a linear regression, don't be disheartened if your value of R is, say, just 0.45. You have still found some kind of relationship. Now, many of you might remember from, say, a psychology class or some other class, the phrase, correlation does not equal causation. That obviously will hold true in this course as well. And the classic example of that is given the one of ice cream sales and shark attacks. Ice cream sales go up during the summertime, as do shark attacks. It doesn't mean that buying an ice cream is going to make your head get bitten off by a shark. For one thing, some people don't have heads to bite off to begin with. But more importantly, it's because more people are at the beach to begin with. If the percentage chance of being bitten by a shark is the exact same, if you have more people at the beach, you're going to have more people getting bitten by sharks because expected value. There are more people. It wasn't the ice cream causing it. And on the other hand around, just because someone's getting bitten by an ice cream, that'd be kind of funny though. Imagine that. Just because someone's getting bitten by a shark doesn't mean, oh, I know, I'm going to go buy an ice cream. They can't. They're probably bleeding out and unconscious. So just because two things have a strong relationship, it doesn't necessarily mean that one causes the other. The math will tell you how strong a relationship is and how much variance is explained by, for one and changes in the other, but it doesn't mean one of them is causing it. You're going to have to use common sense in the real world to assess whether or not they're just simply related or if one is causing changes in the other. So to use the example of the house, common sense will tell you if you add more bedrooms to a house, that should be increasing the price. On the other hand, oftentimes, if you're looking at rentals for homes, usually rental prices are higher during the summer than the winter. But that's not because the Earth, being on the opposite side of its orbit in the sun, suddenly makes the houses more or less valuable. That didn't make any sense. Rather, it's the fact that there are more people looking to buy or rent homes during the summer, say because it's the end of a semester, people are moving out, others moving in, or maybe from the perspective of the person renting out the house, there are more costs associated with move-ins or what have you, and so they look at that and they think, I'm going to increase the rent price as a consequence. So it merely being June doesn't mean, oh, this home must be more valuable because it's June, but rather there are extraneous factors impacting the home price. So when you're dealing with correlation coefficients and R-squareds, just always keep in mind you're going to have to use common sense to assess whether or not the values are simply correlated with each other, hence correlation coefficient, or if one is actually causing a change to occur. This is another reason why notice how in our phrasing we say the amount of variance. We don't say it is changing it, we just say there is an associated change. You might say, Professor, what's the point with all these technicalities? The reason why is because if we give the wrong impression, as could be easily seen with media outlet reports or social media comments or anything of the sort, it's easy to get a completely mixed up view of what's occurring despite the data all being correct. It's not just about getting the computations correct, but getting the interpretations correct as well. And so for the remainder of this lecture, it's going to be mostly interpretations that we go over. For this course, For correlation coefficients in R squareds, for the purposes of the Unit 4 test, the practice test, and web work, you'll be either given R squared or given R. And so it'll be very easy to compute the other. If you're given R squared, you just simply square root it to get R. And if you're given R, you simply square it to get R squared. Now you might say, okay, fine, but I have one more question. Why is this from 0 to 1? Why not negative 5 million? Or positive 100,000? Well, here's why. First of all, notice we're dealing with the absolute value of R. So R, to use the exact notation, is going to be somewhere from negative 1 to positive 1. You might say, fine, why? Well, simple. This is a percentage. It's negative 100% to positive 100%. If the value of R is 100%, what does that mean for R squared? Well, notice if we square our two extremes, then that means our R squared is going to have to be somewhere from negative 1 squared, which is positive 1, so 100%. And if we had 0, it would be 0. 0 to 100. So the domain restriction on R comes from our domain restriction on R squared. Well, to use the correct brackets, let's take the parentheses out. Should be literally brackets like above. There we go. Remember back in Unit 2, we can't have a negative probability or a probability over 100%. And so by definition, the same occurs for R. You might say, fine, why do we have negative 1? Because two values can be inversely related. If the R value is negative, then two values are inversely related. And if it's positive, then they are positively related. And so that's where that domain restriction comes from. So with that, we're going to go over to two final practice problems, each with their own part. Go ahead and when doing these, take a moment to work through them. We will go over the examples and the answers, and then that will finish out today's lecture. All right, so let's start, and I'll use red here, with part A. So here we're just interpreting the value of R in the context of the example. So here, because the value of R is from 0.4 to 0.6, it is a moderate relationship. And the value of R is positive, so we'll say there's a moderate and positive relationship between the number of hours spent studying and exam scores. And to make it a full sentence, there's that. Now for the second part, we need to compute and square it. If you take 0.543, put it in your calculator, and you square it, you are going to get a much less impressive 29.485%. So we'd say 29.485% of the variance in exam scores is explained by changes in the number of hours spent studying. There's something very important to note here. Do not flip these around. Do not flip those. That'll show up as an exam option and you will not get full credit for it. And the reason why it doesn't make sense to flip those is simple. Suppose that we said, I'll use 30% here to round it, 30% of the variance in hours spent studying is explained by exam scores. Well, that doesn't make any sense. If someone scores 1 point lower, we're going to go back in time and change the number of hours they spent studying? That doesn't make any sense. So the good news for you is when you're working through these problems, if you, for some reason, get it a little bit mixed up which goes first, just use some common sense and ask yourself, does it even make sense for one of these to cause the other to change? That's especially true with the second practice. So for this one, again, starting with part A, 0.844, that is a very strong relationship. Again, it's a positive number, so we'll say there is a very strong and positive relationship between the outdoor temperature from April to October in Lubbock and electric bills And then for part B, if you take 0.844 and you square it, you're going to get, rounded to the third decimal place, 71.234% of the variance in the electric bills in Lubbock from April to October is explained by changes in the outdoor temperature. From this one, it's really easy to use common sense to see why flipping it around would look so goofy and stupid. Suppose we flip that around and we said 71% of the variance in the outdoor temperature is explained by the electric bills. So, to understand that correctly, if we just choose to spend less on our electric bills, then the outdoor temperature is going to drop by 10 or 20 degrees. I'm going to tell you something. If we could have done that, I promise we would have done that by now. Clearly, it makes no sense to do it like that. It's the other way around. It's the changes in the outdoor temperature that's going to affect the variance in our electric bills. Now, in this one, you could pretty obviously say, oh, well, yeah, one's causing the other. Temperature goes up, AC needs to be on longer, so of course the electric bills are going to be higher. And that makes sense. A lot of times, it won't just be a correlation, it'll be a causation. But again, just keep in mind, sometimes a correlation is a correlation and does not mean that one thing is causing a change in the other. So when going through the correlation coefficient and the R-squared interpretations, ensure that you correctly state which could be impacting the other, and always keep in mind, correlation is correlation. Unless we have strong evidence that one of them is outright causing the other to happen, as much as we might like it to be, in the case of a math class, we just stick with keeping the wording like this. As mentioned before, we stick with the numbers we get and the results we get from that, and then we can go from there. So that's all for today's, well, for you maybe it could be more than one lecture in one day, depending on when you watch them lecture. So I hope you have a great rest of however much time is left in your day, and assuming you're watching these 13 before 9A, 9B, and 10, then I will speak to you in the Chapter 9A lecture video.